Okay, so in this video, let's understand what the cross-validation and the k-fold cross-validation methods are and what they're used to do. So in any machine learning pipeline, before you start the training, what what is usually done is that you have your data set, which I'll call D. This is your entire data set. You divide this into D train, and then you divide this into, and the other part of this is D test, right? And how what does this do? So I'll take for this particular example, I'll take the example of KNN, the technique KNN, K nearest neighbors. If you don't know the technique, just watch my video on KNN. And but this method can be generalized to any other technique. Okay. So what is usually done is that you take D train and you train your model on D train, and then after training it on D-train, you use D-test to find the best hyperparameters for your model. So in case if I have KNN, right? If I take the example of KNN, D-train helps me find the function. So look, any machine learning model is about finding this function that gives you the best output for your input. So D-train helps me find the nearest neighbors in KNN, and D-test helps me find the best hyperparameter, which is the value of K, right? That's how this usually works. Now, is this a correct way to go about this or not? Well, you could argue that this is probably not correct because, to make this function for the model, it should generalize very well on unseen data or the data that is supposed to come in the future in real time. If your function or if your model cannot generalize well, if it cannot generalize on future data, then this model isn't very useful, right? And how do you know if it generalizes well or not? Well, there's no way to tell because you've used your entire data set to train the model and to find the best hyperparameters. So there's no way to tell if this model will generalize well or not. Although what we do is while finding the K value using D-test, you might have a performance metric like accuracy, where you're seeing the number of points that are classified correctly. Okay? That are classified correctly. Right? That's how you would do. You would see how many number of points give you the maximum accuracy for what value of K, and you would use that value of K in your for your model. But you see that the value of K that you've used was has come from D-test, and D-test is a part of the training data. Then how do you know that your model will generalize well on future unseen data? See, that is the main point. The main point of a machine learning model is to not overfit or underfit. It has to generalize on future unseen data. So in order to overcome this problem, what we usually do is instead of dividing your data set into D-train and D-test, we divide it into three parts. We divide into D-train, D-cross-validation, and D-test. Okay, that's what we do. So if the problem again depends on finding the function for KNN, I'll use D-train to train the model and find the nearest neighbors. I'll use D cross-validation to find the value of K, which is the to find for what value of K do I get the best value of accuracy. And then I will test, as a sanity test, I will test again using D-test to see if my accuracy on D-test is similar to the accuracy I received on DCV, okay, which is D cross-validation. I'll test to see if accuracy is similar to DCV, to the accuracy that I got from DCV. So the thing is that D-test over here is unseen data. Your model was not built using D-test. So it's like future data, which the model has no idea about. It has never come across this data before. So this can be a good point to understand whether your model generalizes well on unseen data or not, because we use dtrain to find the nearest neighbors, and we use dcv to find the value of k, which is the value of the hyperparameter, and then we use dtest to see if it generalizes well on unseen future data. So this is a practice that is usually followed a lot in industry. We don't just take dtrain and we d-test. We take dtrain, cross validation, and d-test. Now, what happens is, how do you divide the data? In what proportion do you divide the data set? So how is the data set usually divided is that your dtrain, usually this is what is followed. It takes 60% of your data. dcv takes 20%, and d-test takes another 20% of your data. Okay. Now, this is again, it can be problem specific or it can depend on what the company follows generally. This can change from, 70, 10, and 20, or it can be 60, 10, and 30. It can be anything. It depends. But if you look at this, you will have to agree with what I tell you next, because the thing is, dtrain and dcv, when you divide the data, right, into dtrain and dcv, you're giving 20% of your data for just finding the value of k. The thing is, you're wasting a lot of data, right? I mean, you can use six over here. If we have dtrain, we use 80% for training, and over here in d-test we use 20% for testing. Okay, but when you divide it into cross validation, you give 20% of it to cross validation, and that is actually wasting a lot of data for that can be used for training, right? Because machine learning models tend to work better, perform better if they have a lot more data to learn from. And if you just take 20% of your data set away into finding the hyperparameter, it can happen that your model doesn't learn very well from the data that you have in your training data set, which comprises of only 60% of your data points. So, is there a way to overcome this problem? Turns out there is. There's something called the k-fold cross validation, which we use to overcome this problem. That dtrain has very less data. Data is also very hard to extract and to accumulate in real life. So you don't want to waste a lot of data. You want as much data as you can take for building your models. So you don't want to waste the data. So what we do is we use something called k-fold cross validation. What that does is, I'm going to take the example of KNN only. Okay. And what I'm going to do is my dtrain, I'll take 80% of data as dtrain, 80% in dtrain, and I'll take 20% in d-test, right? And I'll divide my dtrain data into four parts. D1, let me just rub this. Yeah, I'll divide my dtrain into four parts: D1, D2, D3, D4. Okay. Now, if I divide into four parts, it's called four-fold cross validation. And if I divide into five parts, it's called five-fold cross validation. So you can take any value of k that you want. In k-fold cross validation, if I divide my dtrain into four parts, the value of k is equal to 4. Okay. And this division happens randomly. There's no way to divide this. We usually divide dtrain into four parts randomly. Okay. So what I'm going to do is I will take the value of k, where k is equal to 1. I will train my model on three of those four parts. Let's say D1, D2, D3, and I will test my model on D4. Okay. And let's say I get a value of accuracy as, let's say, A4. Okay, this is the value of accuracy. So this is dtrain, right? Divided into four parts, and this is D cross validation. We use D cross validation to find the accuracy over here. This accuracy that we get is accuracy from D cross validation. Okay, that we get this accuracy from D cross validation, and we get the value of A4. Next, what we do is for the same k equals to 1 hyperparameter value, we take D1, D2, and D4. And the cross validations data set is D3. And this value of accuracy that we get is given from the cross validation dataset D3, and this is the value A3. Next, again, we take k equals to 1 and we take D1, D3, D4, and here we take D2. And the value of accuracy that we get on the D cross validation dataset, which is D2, let's call it A2, sorry, A2. Not A4, it's A2. Okay. And then again, k equals to 1, we take D2, D3, D4, we test it, we find the best value of accuracy on D1, which happens to be a cross-validation data set, and we get A1 over here, right? So this is how cross-validation works. So now we have 4 values of accuracy, and we have tested this value of accuracy on all the different points in our data, D4, D3, D2, D1, right? We have taken each part of our data as a cross-validation data set. Next, what we do is we take this data, we take all of these accuracies and we find the average. Okay, this is average of all of these 4 accuracies. Let's call it A k equals to 1. And this is our final value of accuracy for this trained data set, for this DCV, sorry. Next, when we take k equal to, let's say k equal to 3, right? Again, we follow the same method. We take D1, D2, D3, D4 is our cross-validation data set. We get, let's say we get A4 dash. Then again, for k equal to 3, we take D1, D2, D4, and we get D3 over here, and we get A dash 3. Then again, for k equal to 3, we get D1, D3, D4, and we get D2 over here for a cross-validation data set. We get A2 dash. And then again, we take k equal to 3, we get D2, D3, D4. We take DCV over here, which is D1, and we get A1 dash. Again, we take, we take the average of all of these accuracies for k equal to 3, and we take this as our accuracy value. Okay. So what happens generally is that when you have a training data set, right? And if my y-axis is my accuracy and my x-axis is my value of k, and when I'm testing the accuracy on DCV, I've trained the model on DTrain and I'm testing my model on DCV for k equals 1, 2, 3, so on and so forth, all the way to n. So my graph looks something like this. There is a value where my accuracy is at its maximum, and as the value of k increases, my accuracy starts falling. Let's say that this is 0.9. Okay, that's the value of my accuracy. So over here, what we do is for k equal to 1, we take A1 average, okay, for k equal to 1 average. Then for a equal to 3, we take a k equal to 3 average, whatever we found over here, right? A k equal to 1, a k equal to 3. This is how the accuracy graph looks like for different values of k, and for how the accuracy changes with different values of k. This is how it generally looks like. So for whatever k, let's say this value of k over here is 5, okay? We get the maximum value of accuracy for that value of k. So we take k as our hyperparameter, and then we test using d-test for the same value of k, right? We test using d-test, and we try to see how much does the accuracy vary when compared to the accuracy that we receive from our cross-validation dataset. This shouldn't vary a lot if your model is generalizing well. If it varies a lot, if it's too high or if it's too low when compared to your DCV, which is your D cross-validation dataset, then that means that your model is not it's not generalizing very well. All right. So this is important to understand. This is how your graph looks like for accuracy as k increases. Generally, that's how it looks like. Okay. Okay, in to continue with the previous topic, which was cross validation, I also want to explain how the graph varies with overfitting and underfitting. So, look, I can take this value of error. I can say that error is equal to 1 minus accuracy, right? Accuracy is basically the number of points that were classified correctly upon the total number of points, right? This is my error. Sorry, this is my accuracy, and 1 minus this is my error, right? So, how does the plot of D train and D test change as the error increases or decreases, or the hyperparameter k changes? So, I'll take error on my y axis and I'll take the value of k, which is my hyperparameter, on the x axis. So this is 1, this is 3, this is 5, so on and so forth, all the way to n. So if I take the value of my training dataset, how my training dataset performs as the value of k increases and what error does it give me, I will see that k, as k increases, this is how my d train performs. Okay, this is the error that my d train gives. This is d train, and dcv would look something like this. Okay, this is DCV. So this area is called the area where the model underfits. I'm sorry, it's not, it's the place where the model overfits, right? Because this is a place where your D train performs very, very well. Like it's giving almost zero error. But your DCV cannot generalize very well. So this is the place where it overfits. Now, as K increases, neither D train performs very well or DCV performs there very well, right? So this area is called the area where it underfits. Okay. So when you try to find the value of k, you would generally want something over here in the middle where neither k is very high or neither cv is very high. DCV error from the cross validation dataset is very high. Similarly, yeah. So this is the place where you would want to take your k from, and this is just a general graph that you should consider. This is the called the error plot, and yeah, this basically tells you where the model overfits and where the model underfits.